Here we are with part 2. We're going to go over the intermediate value theorem and a few more examples of how limits don't exist. And yeah. So let's look at this situation. Suppose that you have a continuous function on an interval from x equals 1 to x equals 5 here, and that the y-coordinate when x is 1 is 12, and that when x is 5, y is 8. That's what this says. So can you conclude that there exists a number in the between 1 and 5 so that h of c is 10? So let's think about that. I'm going to try to graph this situation. Okay, so we know that f of 1 is 12 and f of 5 is 8. So we have those points. And we want to see, is there a c somewhere in between x equals 1 and x equals 5 so that the y-coordinate in here is 10. So what that would mean is that there would be a point here where the y-coordinate is right here. That's not a very good dotted line. That's not much better. But anyways, we're talking about that line there where y is 10. Now, because it's a continuous function, you have to be able to draw the graph of it from here over to here somehow. And you can probably see by now that you don't know what it's actually shaped like. Maybe it goes up for a while and then it comes down, or maybe it squiggles around a whole bunch and then goes down here, or maybe it goes down right away and comes back. But no matter what, there's always some point here where it crosses the line y equals 10. So in any of these cases, whichever graph you have, if it's here, maybe your value of c is like 1.2 or something, and here it looks like c is, 3.3, and here c is like 4.8. But either way, no matter what the graph looks like, as long as we know it's continuous, it means that it has to cross that line. So there must be some y-coordinate c, x-coordinate c, so that when you plug it in, the y-coordinate is 10. So the answer to the question is yes. Okay. So that's an example of why the intermediate value theorem applies. So here's what the intermediate value theorem says, is that if you have a continuous function f on this closed interval from a to b, so it's continuous for all these x values, so it looks something like that. And if k is any number between f of a is right here and f of b is right here, then no matter what, the graph is going to have to cross that k. So there must always be some x-coordinate c that makes it so f of c is k for all values of k in this interval. So that's the intermediate value theorem, and it is actually used to prove a lot of other things in calculus. It's pretty important. This class is not going to be very much proof-oriented, but it is important to understand what these theorems say, because there are going to be questions about them on the tests, and they are important for understanding a lot of concepts in calculus. But for this one, okay, so now let's look at showing that a limit doesn't exist. And how can you tell a limit does not exist from the formula? Now, you could either do it by making a graph or doing it algebraically. For this one, I want to look at a graph. And to do this, by the way, we're going to do this sort of in the context of this definition of a limit, that the limit exists only if there's a number L that we can get as close as we want to for all values of x in some very small interval around C. So that's the way we're going to approach these questions. So for this one, if you make a graph of it, it's going to look a lot like this last graph we were looking at. So what you can see is happening here is that when x is close to like 1.8 or 1.9 or close to 2 on the left side, then f of x is negative 1. And if x is on the other side, like 2.1 or 2.2 or something, then f of x becomes 1. And that matters because the limit can't be negative 1. Well, let's actually make a screenshot of this and bring it back. All right, here we are. Here is that graph of that function. So if you say, well, maybe the limit is equal to 1, so is the limit of f of x as x approaches 2 equal to 1? Well, if that were true, then you'd be able to find some little interval around x equals 2 where you go out by delta or in by delta so that you can get as close as you want to 1. So as close as you want, what if I want to get like within 0.2? So here's 0.8 and here's 1.1. So there needs to be a way to guarantee that no matter that, so that for all of the values of x in this little interval, you need to only get things close to 1 between like 1.2 and 0.8. But there's always going to be some values of x on the other side of 2 that make it so f of x is negative 1. And negative 1 is not as close as we want. So like f of like 1.9, for example, is not close to 1. So that means the limit is not 1. Okay. And for the same reason, if you thought the limit was equal to negative 1, there's no way you can make an interval around here so that all of the x values come out to be negative 1, because some of them are going to be 1 if you go on the other side. So the limit as x approaches 2 for f of x is not equal to negative 1 for the same reason. Okay, so what about this one? If you make a graph of 1 over x squared, I'm going to do a sloppy graph real quick. Do this one blue over here. So this graph, well, first of all, my way of remembering what the graph of this looks like is that, well, x squared is always positive. So this is always going to be 1 divided by a positive number. And we also know that when x squared is close to 0, then 1 over x squared, that's going to be 1 divided by a small number. That is very big. So like, for example, if x is, let's say, let's say we want to find g of 0.01, for example. That's going to be 1 divided by 0.01 squared, which is 1 divided by 0.0001, which I think is 10,000. So if you plug in numbers close to 0, you get a really big result, which is why it has an asymptote there, which is a good thing to know. So with this, if you plug in values of x that are like close to 0, like 0.01, the result is just going to get bigger and bigger. So no matter what number you try to get closer to, even if you think the limit is 10,000 or something, then you could just plug in something even closer to 0, and the output of the function is even higher than 10,000, and so it's not getting closer to 10,000. So in this case, we say the limit as x approaches as x approaches 0 of g of x is equal to positive infinity. This is more what the next section, 1.8, is about. But basically, you can think that that infinity is up here, and that as x gets closer to 0, the y-coordinates go there. So you can either say this is equal to infinity, or you could say that it doesn't exist as a number, because there isn't actually a number that it gets closer to. So you can say that, or you can say the limit as x approaches 0 of g of x does not exist. That's my abbreviation for that. And this is really a more correct answer. This infinity thing is kind of like a weird notation for a specific kind of the limit not existing. Okay, this next one is a weird one. Sine of 1 over x. So let's try to analyze what happens to this function as x gets close to 0, kind of from the inside out. So first of all, let's start with the 1 over x. So let's say we're just talking about positive numbers. As x approaches 0 here, let's remember what's going to happen to 1 over x. 1 over x is going to get closer to either infinity or negative infinity, depending on whether x is positive or negative. So the smaller x is, the bigger 1 over x gets, and it keeps growing without limit. So then let's think about the sine function. So if I just had like sine of theta, I'm not going to use x because it's going to be confusing. What happens to sine of theta as theta approaches infinity? And the reason I'm asking this question is because theta here is standing in for 1 over x. So what's happening to the input into the sine function? The input into the sine function here is approaching infinity as like we have here. It's approaching infinity as x approaches 0. So what happens to sine of theta? Well, the graph of sine goes up and down forever. It looks like this, yada, yada, yada. It's not getting any closer to one thing. So sine of theta oscillates. It doesn't approach anything. So that's the answer. Sine of theta approaches nothing. It goes up to -1 and then back down to 0 and then up to 1 and you know what I mean. Sorry, between -1 and 1. Anyways, so let's look at what the graph of the function we're really talking about here looks like. This y equals sine of 1 over x. So instead of this going up and down forever as theta approaches infinity here, that's actually happening as x approaches 0. So as x approaches 0 here, what the graph is going to do is it's going to go up and down more and more times, faster and faster, forever and ever, going between 1 and negative 1, and I'm going to stop going up and down here because I can't do it forever times. But then the similar thing happens on the other side. Either way, the whole thing always stays between y equals 1 and y equals negative 1. So this is a weird example because it is approaching every one of these numbers in between here an infinite number of times as it goes up and down forever here. Just like sine of theta goes up to 1 an infinite number of times, and it goes to negative 1 an infinite number of times. But the problem is that's not the limit. So if you say, well, maybe the limit is 1, is the limit equal to 1? Well, then that means if I want to get like within 0.1 units or some small number of units within y equals 1, there's no interval of x values that will guarantee that all of the y values are in there. Some of the y values are going to come out of that thing because it goes up and down below here too. So no, the h of x values are not always close to 1 when x is close to, I should say, all right, so that is the last thing we need to do in this lesson, right? Yeah, so limits are kind of weird. You might have had an intuitive understanding of them before in pre-calculus, but as we can see, there's some weird functions out there that maybe you hadn't thought about. What do you do with these kinds of functions? Do they have limits? So now you can see why limits sometimes don't exist. Important facts about continuous functions in here you need to know. And yeah, I think we are done. So I'll see you in class later.